quick words. Yeah, you know. So good morning, everybody, and welcome to this session, actually dedicated to biometry in Portugal. And so this session was organized by the Biometrics Section of the Portuguese Statistical Society, and Clara Cordeiro was supposed to chair the session. But I'm here. I'm Professor Nuno Sepúlveda, and I'm from the Warsaw University of Technology, and I would like to introduce you to our two speakers, and Patricia Soares and Ana Martins. And you will have, I guess, 15 minutes. I don't know if you have time for questions or what, but so who's...
So I can start sharing maybe the slide?
Yes. So Patricia will start, and thank you for accepting our invitation to be in this session.
And so everyone can see the screen, okay?
Yeah, we can see.
Okay, thank you for the invitation. So I'm going to, my talk today is about women's statistics and the COVID-19 pandemic, just to give you, okay, just to give you a brief overview. I mean, the COVID-19 pandemic, everyone knows about it. I don't need to go into much detail, but the idea was at the beginning, we didn't know much about it. We didn't know how to spread the transmission, how to stop spread the transmission, which public measure to implement it. We didn't have a vaccine yet. So we needed science-based evidence at the beginning. Well, we always need science-based evidence, but we really needed science-based evidence. And that led to the need, and I guess for some people, the recognition of the importance of statistics, epidemiology, and the data science as well. So again, not to go into much detail about the COVID-19 pandemic, this is the number of cases worldwide and the number of deaths per week. As you can see at the beginning, the number of cases weren't as high as then they were, but it was still a bit worrisome, especially the mortality rate was very high. So we needed to do something to stop the spread of the transmission, and so that's why some countries started to implement restriction. So this is the COVID-19 containment index. It's an index of several measures, restrictions, social distancing measures, closures, and just a few countries are in this figure. But you can see that this is for the year 2020, and you can see that later on the restrictions were more heavier, and we needed to understand more about this. What can we do are these public measures efficient, effective? So what can we do to stop the spread? So that at the time I was at the National School of Public Health, where the dean was Carla Nunes, and so that's obviously, she started thinking, well, we need to do something. It's a school of public health, so we need to start also organizing ourselves to answer a few questions that may appear. So in Portugal, the government started to do regular meetings with a few schools and institutions. Some of these meetings were open to the press, and others were only with the Ministry of Health. So we also participate in these meetings. And the National School of Public Health at the time started the COVID-19 barometer, which started in a few teams, so more to track the epidemiology of COVID-19, the social behavior and perception of the population, as well as some policies and intervention that were being implemented. As you can see, there was a very large team just at the National School of Public Health of more than 30 researchers from different areas. So it was a very multidisciplinary team. And well, what's the role, or what was the role of statistics in the pandemic? I mean, there are a lot of different topics that were approached during the pandemic, but some of them, let's say, more renowned and that we also participated. So to track the spread of the virus, obviously you have the SIR models, which we did not work on, but they were also very important to understand more about the virus. Spatial modeling, which is important to understand the spatial distribution, understand risk factors, who is more at risk of having an hospitalization, so you can use prediction models or regression models. And then obviously public behavior, if the public is adhering to the measures, and health policy evaluation, are they being effective or not? And to do this, we also use different methodologies, so development of surveys and analyzing, longitudinal analysis, since it's over time, to evaluate different measures, interrupted time series or mixed models. And obviously, when we started seeing the vaccine, we need to understand whether there was any hesitancy, people were refusing or not, what can we do about it, who is these individuals that may be hesitant to take the vaccine. And this is also true for every vaccine, its effectiveness. So once a vaccine is out there, we need to continuously monitoring the vaccine. And to do this, we also use regression models, survival analysis, meta-analysis. So this is just a few, an overview of the different methodologies that were used. It's nothing very complex, but it's a more applied perception, perhaps, of what was done during the pandemic. And all of this obviously was used to inform public health decision. So since we had regular meetings with the government, they needed to know as well what could they do, how to adapt their measures, and that was what we were doing at the time. So just a brief overview, in terms of spatial analysis of COVID-19, we use data from COVID-19 notifications from the Portuguese health authorities. There are several different methods to do spatial analysis. In this case, we use something quite simple, spatial scan analysis, just to test whether there was any clusters, comparing the expected incidents with the observed incidents. And we did weekly maps of the relative risk. So that was also something that the government was quite keen in understanding. And sometimes we also adapted. I remember there was an outbreak in the Lisbon area, and then we did something very specific for Lisbon with a finer scale for them to understand what was happening at the time. Regarding the monitoring public behavior and risk perception, at the beginning of the pandemic, we developed a questionnaire that was shared online with a huge adherence. At least at the beginning, people were very keen to share their perception and their motivation and what they were feeling during the pandemic. This was online during more than 2 years, so really during the pandemic. There were several topics approached: risk perception, healthcare use, adherence to public health measures, vaccine uptake. And to do this, we needed data management skills. So this was quite a large amount of data, and we needed to understand how to combine, since this was a longitudinal survey, we need to understand how can we combine this data, what's the best way to create data sets for analysis. And this is only possible for those, especially this part was only done by statisticians. So we need also statistical skills, and several methodologies were used: logistical regression, ordinal multinomial regression, mixed models. So again, nothing very complex, but it's important to have someone that understands and knows how to use and which is the best model to use. Just to give you an overview, this had national coverage, but because again, since these were teams that were presented at the open meetings with the press, they always did some news on what was being analyzed. And we also had scientific outputs as well to inform the scientific communities of what were we finding. Something that was done as well since the beginning of the vaccine, not at the National School of Public Health, at the National Institute of Health in Portugal, was to measure vaccine effectiveness. As you can see, this is a project which is funded by STC and has a lot of European countries. And the objective was to estimate COVID-19 vaccine effectiveness, and it's still ongoing. At the beginning, it was also to estimate against SARS-CoV-2 infection. Nowadays, we only focused on hospital admission and mortality. And some of the statistics that we use survive an analysis, because vaccine effectiveness, it's 1 minus the adjusted hazard ratio. For instance, sometimes we also do, we also estimate vaccine effectiveness for subgroups, for children, and for children, since there was a, well, fortunately, hospitalization was a rare outcome in children. We also use inverted probability of treatment weighting with propensity scores. And since each country, obviously the data is analyzed in each country will produce a vaccine effectiveness estimate, which is shared as well with the national authorities. And in our case, then we need to create a pooled vaccine effectiveness, and we also use meta-analysis with random effect models. Just to give you an overview, this is from this year, and you can see the pool vaccine effectiveness for 2 different age groups. So just to conclude, I think it's quite obvious the need for statistics, especially during these complicated years that we all lived in. Nowadays, I think we still need statistics, especially we need to think about what can happen next pandemics. We need to start thinking about early warning systems, predictive modeling, and we also need, every time that something happens, we also need to evaluate the public measures that are in place. We need to continue to monitoring behavior of the population. Are they adhering to the measures? If not, what can we do? What can we change? And obviously, for any vaccine, we always need to continue. This is also done for any vaccine, influenza, COVID. We need to understand whether hesitancy is increasing or not, and its effectiveness. And for all of this, obviously, we need data management and statistical skills. I'm focusing a lot on data management because this was something very difficult at the time. Not a lot of individuals in our group at the National School of Public Health were able to be able to lead with such a large amount of data. And I think for us statisticians, it's perhaps a bit easier, but it's not something that anyone can understand before experiencing the situation. Yeah, so this is the team that I focused only on the women involved in this, in all of these projects that I mentioned at the National School of Public Health and the Institute of Health. And yes, that's it basically. Thank you.
Wonderful overview, Patricia. Now I'll give the floor to Clara, that actually is the chair of the session. Clara, welcome back.
Thank you.
After some technical problems.
Yeah, thank you very much, Nuno. So without further delay, we should move on to the next speaker, which is Anna. So Anna, could you please share your slides? So Anna, you have about 12 minutes, okay?
Yeah, I can make it, no problem.
Okay, thank you, Anna, thank you.
Let me just here put it. So good morning, everyone. Thank you so much for having me. Today I'll be talking a bit about spatiotemporal models for time series of counts. And I will first start with the motivation for this topic. So time series of counts are in fact non-negative integer values, such as Patricia was presenting before, the number of COVID cases. Those are count values. And that's an example of a very important area where we have this type of data. And when we're dealing with low count values, these have specific characteristics such as asymmetry or an excess of zeros. For instance, here I have the number of daily hospital admissions due to the respiratory causes, and we can see that these values range from 0 to 25. And here we have the histogram, and we see that the data is somewhat skewed. And so continuous models, on the one hand, do not ensure the discrete nature of the response, and they are also of limited approximation in this case due to the normal assumption due to the normal distribution assumption, which is a symmetric distribution. And so it have appeared mainly two different classes of models to deal with this type of data, which are the integer generalized autoregressive conditional heteroscedasticity models or thinning-based models, and I will be focusing on this class of model. So the in-ARMA models, if you know ARMA models from Box and Jenkins, these are more or less similar. But so we have the autoregressive component, which says that our observation at time t depends to some extent of the past observations, and then a moving average component, where we also plot, which is an innovation term, so a random error. And then here in the integer case, our innovation is an IID discrete process. And in contrast to the continuous ARMA models, instead of the multiplication, we have this operation, which is called binomial thinning operator. And what is this operation? So this is in fact a sum of I from 1 up to x, where x is a random variable of IID Bernoulli random variables with a given probability of success. So in the boundary cases, so if the probability is 0, the operation will return 0, and if the probability is 1, the operation will return x itself. But unlike the multiplication, which is deterministic, we run the operation now in our software, we can get the value 1. But if we do it again, we can get value 2. And if we do it again, we can get, for instance, 2. So this is a random variable, which will have, if we repeat this a number of times, we'll get this kind of distribution. And just to introduce another property, the associative and distributive property, they apply, but the distributive property just to some extent. The two probabilities, they're not necessarily a probability, and so this does not apply. And of course, these properties, they are in distribution because we get a distribution from this operation. And so the model that I showed you is a univariate model. And so now imagine that we want to model the same process, but at different locations in space. And so we would like to have a model that connects this information together. And to do that, what I did was to develop this new class of model called the spacetime in ARMA. So the equation seems a bit more complicated. We have, it's again this autoregressive component, and on the other side we have moving average again, but now we have here the summation in both components that are in fact the spatial orders of the model. And these are connected, and now the innovation here is a multivariate process, discrete process. And here the spatial information is introduced in the model through these WL matrices. Okay, yeah. And now instead of having the univariate BTO operation, we have a matrix BTO operation because this W is a matrix. And so how can we operate how can operate between the vector and between the matrix BTO and the vector? It's in the same fashion as multiplication between a vector and a matrix, and this takes advantage actually of the definition of the univariate BTO that I showed you. So here we have each one of these operations is the univariate BTO, which are assumed to be independent, to be easier to deal with from a theoretical point of view. Okay, with regards to the innovation process, just very briefly to say that we use assumptions as usual, so finite moments with regard to the mean and the variance, and we assume this to be independent and identically distributed in time, but not necessarily identically distributed in space, because we can assume different moments for the different but we assume that so that the innovation, it's the simplest case where all of them, they are independent, discrete multivariate innovation. That's it. With regards to the weight matrix, I just want to mention the W matrix that you saw in the equation, and this should reflect the hierarchical order of the spatial neighbors. And so the two locations are neighbors, or 0 if they are not neighbors. And I'll show you just a brief example. So let's assume that our weight is, if two locations are neighbors, we'll give 1 over the number of neighbors. So for 0 order neighbors, we have the identity matrix because each location, it's a 0th order neighbor. For first order neighbors, for instance, consider site 2. It has site 1 and site 3 as first order neighbors. So we give each the weight of 0.5. And for second order neighbors, only site 1 and 3 are second order neighbors. So each gets a weight of 1. But doing this is a bit inconvenient if we are dealing with many locations, because it's difficult to establish which is first orders and second order neighbors. So this is highly subjective. And an alternative can be to consider all locations are first order neighbors, and we can use a metric such as the inverse of the Euclidean distance to construct this matrix. So for instance, here, let's assume we would have these distances, and we could construct a matrix like this. But in general, this matrix is not symmetric because we need to row normalize for estimation purposes. And so that is it. And now I will very briefly focus on the purely autoregressive model. And considering that all locations are first order neighbors, so this part is set to 0. And if we consider only that first order neighbors, we'll have 2 components, one that is purely temporal, so that we depend on each location itself, and then the spatiotemporal component that's depending on the neighbors. So of course that we need estimation approaches to fit the models. And I will just very briefly mention that we developed a tree. So we have to estimate S+2 target parameters. So the S are from the innovation, which in this case I consider to be Poisson. And then we have the probability parameters, the temporal and the spatiotemporal. And of course, we have method of moment, which is quite nice, which has a closed form solution, is super fast to obtain. And then we can either go for conditional least squares or conditional maximum likelihoods via optimization processes. And here is just a picture from simulation study. You can see that as t increases, the mean of in this case here, the median, yeah, of the simulated patches approaches the theoretical value of the parameters. And in general, all methods seem to perform in similar way to each other. And so just briefly an application. So I have here hospital admissions in these areas that you see here. These are the count time series, the corresponding ones. Almost all vary from 0 to 30, but here this one is a bit higher. And what I did was then to fit the models, and we can see that both the temporal and the spatiotemporal parameters are statistically significant, which advocates for the use of this model. Of course, that for time constraints, I did not present here, but we could then do the validation of the model and analyze its fit. So this is it from me. I think I'm able to stick to the time limit. I'm sorry if it was a bit too fast, but I was a bit concerned with getting the time right. Thank you so much for having this initiative, which I think it's quite amazing. Thank you.
Thank you, Anna, and thank you also for the 12 minutes only. So I would like to thank you everyone, and especially I would like to thank to Anna and to Patricia to be here. And so with this, I will end the section number 18. Okay, thank you everybody.